So let's move on to an example, an interesting example that we're going to do based on the central limit theorem. So let's assume that this is Earth, and let's assume that this is an astronomical lab actually, so it's an astronomical observatory, and this guy is an astronomer. So, and he has access to a very good telescope. So what he wants to do, he wants to measure the distance between the Earth and a very distant star exactly. Okay, so he wants to have an exact measurement of, or a very good measurement of the distance between a distant star and the Earth actually. So he has some method, but he's facing one trouble. The trouble is that a good number of times when he makes an observation and tries to compute the distance between the star and the planet, okay, there are some what you call atmospheric things, say around the Earth, that kind of distort this observation actually and produce an error actually. Okay. So the atmospheric conditions outside in the space and say around Earth can produce an error in computing the distance between the Earth and this distant star actually. By the way, he wants to measure the distant star in this distance in light years, and light years is the amount of distance that light covers in the one year actually, one lunar year. And we also know that the light in a distance covers around 3 × 10⁸ kilometers per second actually, so it moves with very high speed actually. Okay, so what to do? So he has a plan actually to have a measure of a good measure of distance between Earth and star. So what he says that let's make a lot of observations of the distance between a star and what do you call Earth, and take the average of those observations, okay, and treat that average as the actual distance between the star and what do you call Earth actually. So for example, so let's assume that x1 is the first measurement of the distance between a star and the planet Earth, and x2 is the second measurement of the distance between a star and the planet, and so on and so forth. The question that really he wanted to, so let me mention say some of the assumptions. So the assumptions on these observations is that all these observations are independent of each other actually. Okay, they are independent of each other, and they are not only independent, but they are identically distributed as well actually. So all these observations are random, independent of each other, and have identical distribution. And let's assume that the average of these observations, he wants actually that the average of these observations should be this actual distance actually, the distance d. D is really the actual distance, okay, between the star and the planet, okay. And he assumes, based on his previous observation, that whenever he makes what do you call an observation, okay, the variance in his observation of the distance between a star and the planet is usually 4 light years actually, okay, 4 light years. So this is the piece of information that we have about, say, these observations. So the question that he wanted to answer, okay, so he says that what n, which is basically number of observations, okay, he should make, what n he should choose so that he can say with say 95% confidence or with say 95% probability that the error between the average of the observations and the actual distance should be no more than 0.5 light years actually. Okay, so the 0.5 is measured in light years. So he wants to compute what you call this n, okay, such that the probability that the average of the observed distance between a star and planets and the actual distance between a star and planets, the difference between them should not be more than 0.5 light years actually. So he wants this event to happen with say 95% of the confidence or the 95% of the probability. The question is, what should he choose n? In other words, how many observations he should make, okay? How many observations this astronomer should make so that he can say with a 95% of the confidence that now yes, the distance, the actual distance between star and planet and the average distance, average of these observations is no more than they are not different more than they are not differing by say 0.5 light years actually. In other words, the error is really 0.5, it is not more than 1/2 light years actually. So this is what that he want to, what do you call, compute. So he is interested in the number of observations that he want to make. So how can we do it? So the solution can come through what do you call the central limit theorem actually. So for the central limit theorem, we know central limit theorem talks about sum of the observations, okay, observed distances minus the average of the observed distances. So each xi has what do you call average d, so their average is going to be nd divided by, okay, the standard deviation of the sum of these distances, okay. So let's call this what do you call Zn. So Zn is what? Sum of observations of these distances minus, so it's a standardized sum of the distances that what do you call that for example this astronomer has observed actually, okay. And we know by central limit theorem that this guy converges to standard normal distribution, okay, as n gets bigger and bigger. In other words, as number of observations would get bigger and bigger, this Zn will become what do you call the standard normal random variable actually. So let's come to, for example, this probability. So this probability says that that the probability that sum of xi minus n, okay, minus d should be less than or equal to 0.5. This is what that he wants, and I know that this is equal to 0.95. He wants it to be equal to 9.95. I can turn this sum into, let's try to write this expression in the terms of this. So what can I do is that let's take for example LCM of it. So it's going to be minus nd divided by n less than or equal to 0.5. Okay. I can for example multiply with the square root of n on both sides, okay, and in order to convert it into n, I need to make this for example 2, because if the variance is 4, so the sigma must be 2. So let's divide both sides by what do you call 2 actually, okay, let's divide both sides by 2. So now I can say that this guy is the absolute of Zn, okay, and this is less than or equal to 1/2, and 1/2 is going to be the square root of n by 4.5. I can approximate this probability by treating this Zn to be the standard normal random variable. In other words, by treating this as z less than or equal to square root of n by 4, okay, which is same as z being between square root of n by minus square root of n by 4 and square root of n by 4 actually. Okay, this is what it is going to be. Now let's say I know that this probability, so z is a standard normal, so this probability can be computed by, say, the phi, computing the phi at square root of n by 4 minus computing the phi at square root of minus square root of n by 4 actually. And this, I can write this as phi of square root of n by 4 minus 1 minus phi of square root of n by 4 actually, okay, and this will be 2 times of phi of square root of n by 4 minus 1. So this probability can be approximated by this number, okay, and I want it to be how much? We want this probability to be 0.95. So we want this to be 0.95. In other words, for what value of the n, okay, for what value of the n, this probability would be equal to or approximately equal to 0.95. So I can add 1 and divide by 2, then the phi of square root of n by 4 is going to be, you can calculate it, it's going to be 0.975. Now you can go to the table of a standard normal random variable and see that, okay, for what value you get this probability. So you can see that the value for which this, you're going to get this probability is equal to 1.96 actually. Okay, 1.96. And if you square both sides, then it's going to be 1.96 squared times, what do you call, 16 actually. And this number, you can estimate it to be, say, 61 point, say, approximately 41. Okay. Now n is kind of representing the number of observations that astronomer must make. So this observation can't be fraction or should not be fraction. So let's choose this n1 to be, what do you call, 62. Okay. So the central limit theorem has helped kind of an astronomer to solve a practical problem of finding the distance between a distant star and what do you call Earth. So what does this conclusion is telling us? That this astronomer must at least, what do you call, make 62 observations to say with the 95% of the confidence, okay, with the 95% of the probability that the average distance, average observed distance between a star and the, what do you call, a star and the planet is not different from the actual distance by 0.5, okay, if the number of observations that are made are 62. So he's gonna make, what do you call, 62 observations in order to make a good understanding that how much he's going to do what with this 62. He's gonna make 62 observations of the distance between a star and planet, and then he's gonna compute the average of those 62 observations. So the central limit theorem is telling that this average of the 62 observation is not going to be different from the actual distance between a star and planet by more than by 0.5 light years actually. So it's a pretty good kind of conclusion actually. So you see that a lot of practical science problems, practical scientific problems are being solved through these probabilistic methods actually. Here is another conclusion, another interesting conclusion that you can make through Chebyshev inequality in the same situation. Okay? Here is another interesting conclusion that you can make about Chebyshev inequality. Okay? So another conclusion from Chebyshev's inequality. Okay. Let's compute, say, the expectation of this these average of the observed distances. Okay, then this would be same as the sum of the expectations of xi by n, and I know that that goes from I equal to 1 to n. Okay, then I know that this expectation is d, so it's going to be like summing up d, the actual distance. So this is really d by n. Okay, so this will become nd by n, and this will be equal to d. The variance of the sum of xi that goes from 1 to n divided by n is going to be what? Is going to be the sum of I equal to 1 to n variance of xi, because they are independent, divided by n square. Okay, so variance of xi is 4 light years, so it's going to be 4 n divided by n square, so it's going to be 4 over n. Okay, now let's apply the Chebyshev. Recall the Chebyshev inequality. Chebyshev inequality says x minus mu being greater than or equal to a number a, this probability could be at most variance, which is sigma square by what do you call a square. Okay, sigma square by a square. This could be the at most probability. So now, if I, for example, take this observation, I say that what is the probability? What is the probability that the average of my observations, of the astronomers' observations, the average distance from observations is going to differ from the actual distance of the stars, distance between a star and planet, by more than 0.5 light years. This probability can be estimated by the variance of this, which is 4 by n square. Okay, 4 by n square divided by a square, which is 0.5 square actually. Okay. So it's going to be 4 by n square. No, this is not going to be square. This is going to be simply 4 by n, 0.5 square. So this is going to be equal to 16 by n. Now we want this. So this probability. Okay. So here's something interesting. You can say that this probability can be at most 16 by n. Okay, but so if this probability should be, what you call 0.95, then what should be this probability? So this probability should be 0.05. So in other words, this should be 0.95 to 0.05. So in other words, 16 by n must be equal to 0.05. Okay? And if this is the case, then you can basically deduce that your n should be, so if I divide say by 0.05, should be less than or equal to 16 by 0.05, and you can calculate it to be 320. Okay? So if your observations are less than or equal to, if the astronomer is making an observations less than or equal to 320 and say greater than or equal to what you call 63, then with the 95% of the confidence he can say, okay, he can say that yes, the distance between the my observed average and the actual distance is not more than 0.5 years actually. So from one side, central limit theorem gave you, for example, this bound that your number of observations should be bigger than or equal to what you call 62, but they should not go between 320. So the Chebyshev inequality combined with this gives a very interesting conclusion that if the astronomer is making a number of observations between say 62 and 320, okay, any observations, then with the 95% of the confidence he can say that yes, the distance between the observed distance, the average of the observed distance between the planet and the star is not differing from the actual distance, okay, by 0.5 light years actually. So you got kind of a, you know, number of you got kind of a bound on the number of observations that should be made between 62 to 320. So the more n it is going to be, the more chances are there that you're going to have what do you call this difference not more than 0.5 light years actually. So I hope that, you know, kind of this result helped you a little bit. Now I'm going to just write a generic version of what we will call central limit theorem. I'm not going to prove it. I'm going to just write it and interpret it and talk a little bit about it. One of the restrictions that you have in your previous result is that that in your previous central limit theorem that your entire sequence should be not only independent, but you are forced to say that all random variables should have the same distribution actually. They must be identically distributed. So this version of central limit theorem says that you only need independence. Okay, your all random variables need not to be identically distributed. They can have any distribution they like actually. Okay. So you can say that this is the CLT for independent random variables. Previous was for about the IID level. Okay. So this is more general than previous one. So let you have a sequence of random variables of independent random variables, okay, having means not necessarily same. So the expectation of xi is say mu I, and variance of xi equal to sigma I square. In other words, you have a sequence of independent random variable in which all these random variables can have any distribution. So the one could be binomial, other could be geometric, other other could be normal, so on and so forth actually. Okay. Now if there are two assumptions more satisfied about what do you call these random variables, then you have also the same result as previous actually. So what are those two assumptions in addition? That probability that all of these random variables are bounded is equal to 1. In other words, there is an assumption that all these random variables are bounded almost surely. Okay? And the second assumption is that the sum of these all variances are equal to 1 to infinity is equal to infinity. In other words, that the sum of the variances or sum of the variances is a divergent sequence actually. Okay, is a divergent series. Okay. So I have a sequence of random variables that are independent, having any distribution with means mu I, variance sigma I square. Additionally, all of these random variables are bounded with probability 1, and their sum of their variances is equal to infinity. So their series diverges. Then probability. Okay. Probability that there is standardized version. In other words, compute the sum of say I equal to 1 to n xi minus mu I divided by the standard deviation of say I equal to 1 to n sigma I square. Okay, this random variable less than or equal to a, being less than or equal to a. In other words, this is, so if I call this say random variable as Sn, then this represents the distribution function of Sn evaluated at a converges to the distribution function of standard normal random variable as n goes to infinity. In other words, this random variable, okay, will converge to the standard normal random variable as n goes to infinity. And now there is not any restriction that all these random variables are IIDs, they are identically distributed. In other words, the central limit theorem is also true for general independent random variables actually. So in addition, they should satisfy these two conditions. Okay, so this is kind of called the CLT, the central limit theorem for independent random variables as well. So this is a generalized version. The next thing that I would like to talk about is some inequalities. Okay, some inequalities, some more inequalities and examples, and then in the end I will try to prove what do you call the strong law of large numbers. So let's talk about some more interesting inequalities and their applications. Okay. So here is what do you call one-sided Chebyshev inequality that goes like this. So suppose